Hello, everyone. Welcome to the live session. We are excited to be back with you. It's been a few weeks. My name is Matthew. I am one of the instructors for our online classes and part of the astronomy teaching team. We've got another live session today. So the way that this works is we have you post your questions in the chat. I will grab your questions from there, and then I will organize them and give them to Chris. Please try and ask your questions for like a beginner audience, and ask your questions only once. I'll see everything. We just kind of jump around to make sure we get a variety of questions from a variety of participants. Also, make sure you like and subscribe to our YouTube channel so that you can hear about upcoming streams. Chris, I'm going to hand this over to you to welcome everyone, and then we'll get started with questions.
Okay, welcome everyone to the live session associated with our online classes or MOOCs, or if you found them by another means, that's fine too. Welcome, and you're enabled to ask any question on astronomy, and I'll do my best to answer.
Excellent. The first question from one of our live participants is from Gaetano, who asks, what is your opinion about the Axions particle forming the clumpiness inside the universe that a team from Toronto guided by Rogers thinks might be one of the ingredients of dark matter?
So the axion is a fundamental particle that's part of the landscape of particle physics. The question really is, the particle has its role in mediating one of the fundamental forces of nature, but what's very unknown is what the mass of the axion is. If the axion has a particular mass, then its weak levels of interactions suggest that it could be a dark matter particle. So it's been one of the candidates, maybe not the most favorable candidate, but a plausible candidate for dark matter. The trouble is, these are extremely difficult measurements because of the weak interactions. It's just very hard to tease out what the axion actually does in particle interactions. So that leads to a lot of speculation about dark matter being composed of axions or partly composed of axions, and the Toronto team and result is another part of this discussion. What's missing is sort of clinching evidence from a particle physics experiment rather than an astronomical observation of what the mass of the axion is. So when you're inferring axions from astronomical observations, it's really a very indirect argument. Because the observations really don't tell you the nature of the dark matter. That's been true of dark matter observations in astronomy for 50 years, and this result is in the same category. So it's interesting, but I don't think it has put axions at the center of the debate over what dark matter is.
Excellent. Thank you very much. I have a note that the sound needs to be checked, so I will work on that. My apologies. The next question is from one of our live participants. Adrian would like to know, would a heavy isotope of oxygen be more likely to remain within the gravitational field of Mars than plain oxygen? So, without being blown out into the an interstellar medium, I suppose.
Yes, I mean, mass obviously dictates what kind of gas is retained by a planet of a particular gravitational field. Isotope of oxygen, however, doesn't increase the mass of oxygen. It's just basically adding a neutron. Each particular isotope adds one neutron into the nucleus, and the atomic number is 8. So you're really only increasing the mass of oxygen by less than 10% for the first isotope, and then there are other isotopes that increase it by more. That's a marginal effect, so I don't think it would make the difference between oxygen being retained or not retained globally. Also, you'd have to have a mechanism for generating significant quantities of the isotope of oxygen. Oxygen isotopes on Earth are extremely rare compared to the main form of oxygen that's 18% of the atmosphere that we breathe. So I don't think isotopic oxygen plays a significant role in the Martian atmosphere.
Thank you very much. No, that's very interesting concept and question. And the next question is from Kendra Smith, who asks, what do you think about the claim that astronomy is just advanced astrology?
Well, it's a fairly glib and pejorative statement to say that. It is true in a historical sense that astronomy emerged from astrology. Astrology was a practice that goes back to the Romans. Divination was one of their sort of superstitious practices. The Romans had many superstitions, and astrology went into popular currency in Roman times, initially just for the emperors and then eventually for the common people a few centuries after Christ. So astrology did indeed precede astronomy as a formal discipline, but it's not a science, and so I don't think astrology really led into astronomy in any direct way.
The next question is from one of our live participants. Rion1 asks, how are the equations of fluid dynamics, for example, equations for vorticity, used to understand large-scale circulation patterns of galaxies?
Fluid dynamics is a very relevant field of physics in terms of astrophysics. But when it's applied to cosmology, it's a little tricky because the intergalactic medium, or the large-scale medium between galaxies, is an extremely diffuse plasma. And while in principle it could be dictated by the laws of fluid dynamics, in practice that's a very weak application of fluid dynamics. Fluid dynamics applies much more directly in a situation of a true fluid rather than a situation of a plasma. So fluid dynamics doesn't really work to predict the shapes and distributions of galaxies in large-scale structure.
The next question is from LZL. Can we prove that, quote, everything in astronomy is correct, or is that even a valid question? How confident are astronomers in their field when there's so much that we seemingly might not know?
It's an important point that astronomy has to be careful about being overly sure of making certain statements. So I would say astronomy is a discovery science. There's many things that were not predicted that we've discovered. For example, dark matter and dark energy, two main ingredients of the universe. So astronomers would be wise, given the history of the subject and our discoveries that were unanticipated, to have some humility and perhaps not overstate their confidence that they know what's going on. So astronomy does have a fair amount of unknown areas associated with it, and that's part of what makes it an exciting science, because research is essentially about taking the things that we don't know into the realm of the things that we do know or understand. And astronomy in that sense has made progress over the years. But it is absolutely true that there are things that astronomy has not fully understood, or astronomers have not fully understood, and there may be a few things that we think we know that we don't actually know as well as we thought.
The next question is from Sanchita, who would like to know, can you talk about what a barycenter is and how is it related to the revolution of the Sun and Jupiter?
So bary is the from the Greek root for weight, and it means what's the center of weight or the center of mass of a system. So the barycenter of any two-body system, for example, is the point about which the two objects appear to rotate. And so when it comes to the solar system, where the Sun is the center of the solar system, Jupiter is massive enough to mean that the Sun does not just spin about the center of its axis, but it actually pivots about a point somewhere near its edge. And that point is the barycenter of the Sun-Jupiter system. Now, all the other planets are much more massive than Jupiter, and so they do add complications or epicycles to this center of mass motion. But the main motion is around the barycenter of the Sun and Jupiter, which, as I said, lies pretty much close to the surface of the Sun.
The next question is from Wendy Traver. Can you discuss the cosmic neutrino background, which I read predates the cosmic microwave background?
Certainly. The cosmic neutrino background is a simple prediction of the Big Bang theory, because one of the first phases of evolution of the universe was called baryogenesis, which is the creation of baryons, essentially the normal particles that we're made of, protons, neutrons, and electrons. And in that reaction, just as in a fusion reaction you have neutrinos or antineutrinos created, you have neutrinos created out of the creation of baryons. And so for every baryon there's at least one neutrino. And those neutrinos were created in the first fractions of a second after the Big Bang, about a microsecond actually. And they should exist, they should continue to exist. And since neutrinos interact very weakly, they will have diffused out through the universe as it expanded, and those neutrinos should still be sitting there. They will, of course, have an extremely low temperature at this point, lower than the equivalent temperature of the microwave background, and so they're rather low energy neutrinos, the same flux in every direction, and it is a very difficult background to detect because neutrino detection is difficult in the first place. Neutrino astronomy is still in its infancy, but the neutrino background is probably the main thing neutrino astronomers hope to detect with their next generation of neutrino detectors.
Excellent, thank you. Just want to welcome everybody who has joined us since we started. We now have about 116 people, so we are happy that you are here today with us. And we're going to grab another question from the chat. This one is from Karen, who has a great question I think we can expand on a little bit. Karen says, good evening in the UK. How do we know that the images produced by adaptive telescopes are the correct image and not a corruption of a lesser quality image before the adaptive technology is applied?
Well, adaptive optics, as it's called, which is a mechanism for sharpening up images and essentially taking out the blurring of the Earth's atmosphere due to turbulent motions in the upper atmosphere, that's a quite mature technology. But rather than just assuming it always gives us a better image of the sky, astronomers can actually test this. And one of the ways they test it is by looking at very close double stars or star systems where we know the geometry of the stars and they're close together, and making sure that when you turn on the adaptive optics system, the stars stay at their appropriate separations, and then the images of the individual objects sharpen up. So there's a series of test cases you can use for adaptive optics which demonstrate that it's not introducing artifacts and it is indeed sharpening up the images of objects. And then once you've shown that with these particular calibration objects or test cases, then you can go ahead and use it all over the sky.
It's interesting to me because this has been a problem or a question that people have had since the beginning. There were questions that for Galileo that possibly his telescopes were introducing things into the images. Can you talk a little bit about that history and concern, and then maybe how the most modern telescopes, we have questions about that for um, gravitational waves?
So the history of telescopes is one of continuous improvement of the optics. Now, the first few centuries of telescopes were refracting telescopes, like Galileo's original telescope, and using, poorly made or the best technology of the time available lenses. Those lenses were imperfect. They didn't form very good images. They had chromatic aberration. They didn't focus the light at different wavelengths at the same distance behind the lens. And so there were absolutely optical artifacts and effects that made the images poor. Once astronomers moved to the realm of reflecting telescopes with parabolic mirror shapes, chromatic aberration could be controlled or was gone, and the image quality could be made better just by having more and more accurate parabolic surfaces. So in the modern history of astronomy, there's no indication at all that the telescope optics are introducing artifacts. They now are able to work essentially down to their diffraction limit. When you move into a new regime like gravitational waves, then of course you have a whole new set of problems, and the instrumentation and the method of detection are totally different from electromagnetic waves. So each new innovation in astronomy in terms of types of information or radiation we detect involves its own challenges in being sure that you're not looking at artifacts. But in the realm of optical astronomy, with a long history of innovation and engineering of optical telescopes, the best telescopes in the world are making extremely clean images.
Excellent, thank you. The next question is from Irem. If white holes really did exist and they're, I guess they could be pried open to transport a person, why is it that we don't have any observations of them?
Well, white holes are a theoretical construct, so there's no evidence they exist. That's the simplest statement to make. They're allowed by general relativity, but things that are allowed by physical theory don't have to exist in our universe. And astronomers have found no evidence that white holes exist. They're hypothetically a rift in space-time where material or energy and radiation that go into one part of space-time emerge from another part of space-time, so a sort of counterpoint to a black hole. Now, you might imagine that it's a little hard to decide whether you're seeing an object that's just emitting energy or an object that's a white hole, because it's a cleft in space-time portaling to you to another region. But space-time would have to be actually quite convoluted for white holes to exist, and space-time seems to be extremely flat. And so while we have black holes, which are sort of pinpricks in space-time, self-contained bubbles of space-time caused by extreme gravity, there's no indication of connections to distant or disparate regions of space-time. So I think at this point white holes remain a purely theoretical concept.
The next question is from an email. Christina V, or Christina Vi, asks, what is the physics behind Cepheid variables? Why do they contract and expand?
So variable stars, there are actually dozens of different varieties of variable stars in astronomy. Cepheids are particularly important and were found to be so in the 1920s by Henrietta Leavitt. I was working at the Harvard College Observatory, and she used photographic plates to show that the period of pulsation of Cepheid variables correlated with their luminosity. And this linear relationship between the period of a Cepheid variable and its luminosity was the key to determining the distance to the galaxies. That was done by Edwin Hubble in the 1920s. So very important objects in astronomy history and in terms of measuring distances. The physics of the pulsation is also pretty well understood. When stars reach late stages in their life, and especially if they're more massive than the sun, the energy sources start to fluctuate as they run low on their nuclear fuel or transition to new nuclear fuels. And in this situation, they can have periods of their life, not their entire life, but a period of their late stage of evolution, where in this phase of instability, the fusion rate can vary. And if the fusion rate grows, it'll puff the star out and cause its envelope to expand and its luminosity to grow. Then gravity pulls the material back in, and so the star shrinks and the fusion rate goes down, and then it overshoots, and then this process repeats, almost like an energy pendulum in operation. And that's why you have a periodic variation. And the period of the variation in an almost natural way, correlates with the size and therefore the luminosity of the star.
Shareem asks, is the Big Bang the only possible theory of the beginning of the universe, or are there other theories that might be as accurate as the Big Bang?
The Big Bang is the best theory of the universe and has been for pretty much half a century now. And the problem is not that theorists have not been imaginative in thinking of other ways the universe could have started. The problem is the maturity of the theory and the fact that the fundamental data that it would have to explain, the microwave background radiation, will have to be explained by an alternative theory. And that was the death knell for the steady state theory, which predicts that space expands but the universe is not globally changing because matter is formed in the space between galaxies, and so that's how you get new galaxies and Hubble expansion. So any theory for the alternative beginning of the universe that's not the Big Bang will have to explain the microwave background. It'll also have to explain where the helium in the universe came from, which in the Big Bang comes in the first few minutes when the universe was 10 to 15 million degrees hot. So I'm not going to go through the various, quite radical or speculative alternative theories of the universe, but none of them have cleared the bar of explaining the existing evidence we have, which supports the Big Bang very strongly.
The next question is from Maxwell. How many planets are estimated to have originally been in the solar system?
This is an interesting research question, and the simple answer is we don't know, because the history of the solar system goes back 4.5 billion years, and the early phase of planet formation was a very chaotic phase. It happened apparently very quickly. The formation of the giant and terrestrial planets took place in perhaps less than 10 million years, and that's in a system that's now over 4 billion years old. Now, in that early chaotic phase, it is very easy for creation and destruction processes to be almost balanced. And so while you're building planets by accretion and collisions of planetesimals, you're also destroying planets. So there is good evidence, and papers have been written on the fact that there might have been a fifth terrestrial planet in the early phase that was ejected due to gravitational instabilities. So that's at least a speculation that's in the literature, that there was one extraterrestrial planet early on that got kicked out by instability. And possibly there were more. So it's very unclear because there's no trace right now. It's very hard to find direct evidence that's a straight line back to that early phase. And so this has all been done by sort of inference and by replicating the initial conditions of the solar system and trying to see what might happen when you run a simulation.
The next question is from Ravi, who sent an email. You said in the last session that the moon would be a good place for optical as well as radio telescopes. I can understand radio telescopes on the far side, shielded from the Earth's radio noise, but where would an optical telescope go and not be affected by sunshine for many days a month? Building in a shadowed crater sounds risky even on top of all the other problems.
So on the moon, assuming you're on the dark side, I mean, the main thing you want to protect from is Earthshine. And again, because there's no atmosphere, you're in a very good situation for optical astronomy because you can shield the sunlight just directly with a simple shield. If you try and shield the sunlight on the Earth's surface, then sunlight, of course, is scattering through the atmospheric particles. That's why the sky is blue, because sunlight is scattered, and preferentially those are short waves, and that's why the sky looks blue. That's sunlight that causes the sky to look blue. On the moon, there's no such problem because there's no atmosphere. So blocking or occulting the sun is perfect. You just block the sun's light; it will not reach the telescope. And because there's no atmosphere, there's no scattering of particles. So once you're shielded from the much brighter light of the reflected light of the Earth, because you're on the dark side of the moon, shielding from the sun is no problem. And so you really do have the best optical observing situation you could imagine.
The next question is from Sabnam, who asks, I was curious about the wobbling of stars due to planets. For a multiplanetary system, the wobble, I guess, would be a resultant effect due to all the masses of all the planets. In such a case, how do we identify individual planets? It's
a good question. So people talk about the simple situation of a single planet causing a star to wobble, and the two objects rotate about their common center of gravity, and the period of that motion, it's like a lever arm. The period of the motion is clear, and then the mass is given by this sort of lever arm. If you have multiple planets, you get the same data. So in a multiple planet system, you're still measuring the Doppler shift of the star over time, and it's very elegant how the data reduction takes place, because each planet, whatever its mass, is imputing a sinusoidal variation in the Doppler shift of the star, and it's additive. So smaller planets are adding a smaller sinusoid with a different frequency corresponding to the period of orbit, and basically you just have to take the radial velocity data and subject it to harmonic analysis. You're basically just looking at the various harmonics of the planets, and they just drop out. So you fit the strongest signal from the biggest planet, subtract that out, and then look for residuals that could also be fit by harmonics. And so it's actually quite easy to simultaneously detect and fit multiple planets in one set of Doppler data, and that's how people have been doing this now for 35 years.
Excellent. The next question is from Faisal, who asks, why don't we see rings around the sun since its formation or around the stars has happened with the gas giant planets?
So there was material, of course, left over from the sun's formation, and that is what became the solar system and the planets and the debris of the solar system, like the asteroid belt and the comet cloud. The reason there are no rings around the sun itself is just because the inner solar system, including the region you might look for rings, was subject to fierce radiation pressure especially from the young sun, and the young sun was brighter and more luminous than the sun is now. Went through a T-Tauri phase, as it's called. And so that radiation pressure was strong enough to drive away all particles. So there's no way any particles could survive to form rings around the sun.
The next question is from Hernan Reyes, who sent an email. During a previous question and answer session, you mentioned that it was reasonable to hypothesize that every star in our galaxy had or could have at least one exoplanet. The question is, could a young supergiant, so how does that work around these young giant stars like Rigel? Could they have a habitable zone? And how does that work with these young supergiant stars?
Right. So the statement of one planet per star minimum actually comes as a statistical statement, comes from microlensing surveys, which are very they're a very good way to categorize the overall frequency of planets, because they have very few selection effects. They're sensitive to very small mass planets too. So that's where that comes from, and that doesn't distinguish between the type of star. So indeed, it is likely that in the formation process, the most massive stars, supergiant stars, had planet systems around them. They're not as of much interest to astronomers or astrobiologists for the obvious reason that such stars have very short lifetimes. So the odds of life forming and being able to evolve to any significant degree on these planets are minimal. The separate question of whether even such planets would be in a habitable zone is unclear, because for luminous stars, the habitable zone, in principle, it's obviously very far from the star, and it may be that there's not enough in debris in the gas disk that collapses and forms a star to form planets, even gas giants, that far out. And the truth is, this field has had very little research and very little simulation, because the planets in these situations are not of astrobiological interest.
The next question is from Tanu Sharma, who asks, hello, sir. What is your take on dark matter-free galaxies from collisions like the Bullet galaxy collision?
So the issue of whether there are galaxies without dark matter has come up a number of times. People make observations, because it does seem that there's some global cosmic average amount of dark matter per galaxy that holds for small, medium, and large galaxies. And the ratio of the dark matter to normal baryonic matter is about a factor of 6 to 1. But that's a mean, and there are variations from the mean. And so people have looked for low-mass galaxies which have very little dark matter, and there's certainly some dwarf galaxies where they seem to be mostly baryonic matter. The particular situations referred to in the question, the bullet cluster, is one of the ways we can diagnose dark matter, its nature, and also just the fact that it exists beyond a reasonable doubt, come from situations where clusters collide, which does happen occasionally. The baryonic material, particularly the gas, is viscous or sticky and will collide and heat up and glow in X-rays. Well, the dark matter has very weak interactions, no electromagnetic radiation, and so the dark matter components will pass through each other. And so you can then end up with the baryonic material in the center and the two dark matter centroids of mass forming wings on either side, and that's a bullet cluster in similar situations. Nobody's found a cluster of galaxies with no dark matter. All the largest mass objects in the universe do seem to be bound by dark matter. Smaller objects like galaxies and dwarf galaxies have been found which seem to have very low amounts of dark matter, and it could indeed be caused by interactions earlier in the universe that essentially stripped the baryons off and left you with just the dark matter, or vice versa. So that's the hypothesis.
The next question is from Yang Pachankis, who sent an email and asks, in terms of the application of science, is there a significant, or have you noticed any significant cultural differences between the UK and the US? And then I'm going to add, or between any other, sort of cultures that practice science?
Science is a worldwide pursuit, and then one of the attractions and I think strengths of science is that the community of scientists is an international community. They talk to each other, they meet routinely on whatever topic they're working on. The language of science is generally English, but many scientists speak other languages too. So science is a global pursuit, and that's a good thing. So at the zeroth order, there's no great variation. There's some homogeneity. The language of science is the same. The tools of science are the same, different countries. But yes, in detail, definitely there are cultural differences. There are differences in the way scientists are trained in particular. So the biggest differences in science come from the educational systems of the different countries, I think. The cultures of science and whether different countries are more or less admitting to science as a discipline or as a thing that has high prestige in the culture, that also can show some variations. So yes, there are some quite interesting and subtle cultural differences in the way science is practiced or who practices it around the world, and there's some papers been written about this, but it's a kind of interesting subject.
Next question is from Bakujo123. Can you talk a little bit about what we do know about dark matter? Sometimes it seems like a concept similar to ether. Why is it that we have this idea of dark matter and it's not just some stardust or laws being slightly different than what we know?
So it's a good question to pose, to ask whether after 50 or 60 years our understanding or hypothesis of dark matter is no different from our hypothesis of ether. So ether was the medium in space, pervading all space, through which light was supposed to move. It was the carrier essentially for light and electromagnetic radiation. And a pivotal experiment in the early 20th century, the Michelson-Morley experiment, an interferometer experiment, was able to show that the velocity of light arrived at the same time. The velocity of light was seen at the same speed regardless of the Earth's motion around the sun and its position around the sun. So therefore there could not be an ether through which the Earth was traveling. So there was an experimental result that refuted the idea of an ether, which had been around since the ancient Greek time. There's been no analogous experiment to refute the existence of dark matter, and in fact the astronomical observations have all tended to affirm dark matter, which is to say that there is a component of the universe present on all scales, from galaxies and within galaxies to clusters, superclusters in the universe itself, which exerts gravity but does not interact with electromagnetic radiation. And so there are many types of observation that affirm this. Gravitational lensing affirms it. The way objects move in space within a galaxy or within a cluster affirm this. So it would be very difficult for a single observation to refute the existence of dark matter given the accumulation of evidence over the years. It is, however, possible, just to go back to the original motivation for the question, that if you tweak the theory of gravity sufficiently, move it away from a Newtonian inverse square law, you can obviate the need for dark matter entirely. And so it is true that some theorists have been looking at alternate theories of gravity that would do away with the need for dark matter. Those theories haven't yet succeeded or passed the bar where we know how to confirm them, but they're still in play. So that is an option that's being looked at.
The next question is from Isla Holroyd, who sent an email and is on with us live. Hello, Professor. My question is, how do we know red light from a distant galaxy is redshifted and not red light from a local object?
So the reason we really know that the redshift represents distance is because in the light from a galaxy we have spectral markers that correspond to the elements that the galaxy is made of. So the galaxy is a set of stars and some gas, and that gas and stars are made of primarily hydrogen, helium, and then small amounts of the heavier elements. So we see the markers in the spectra, either in emission or absorption, of the lines of hydrogen, helium, and the heavier elements. And those wavelengths are very particular. In the lab they have particular wavelengths, and when in a distant galaxy you see them shifted to the red part of the spectrum, it really means it can't be a local object. The object would have to have some very large and rapid motion for those spectral features to be shifted. So it's really those spectral markers that tell us that we're looking at a distant object moving at high speed due to the expansion of the universe.
So Yang Pachankas asks, what are the subtle differences between neutrons and neutrinos in particle physics?
Neutrons are fundamental constituents of normal atoms, along with protons and electrons, but they're not fundamental particles, of course. Neutrons and protons are both made of 3 quarks, and the evidence for that came from particle physics experiments in the 1960s, the theory in the 1960s, the confirmation in the 1970s. So neutrons are composite particles with no electric charge, formed with triplets of quarks. Neutrinos are fundamental particles that are part of the standard model and come in 3 flavors: the normal electron neutrino, heavier muon neutrino, and the heaviest tau neutrino. And there's fairly large mass ratios between those 3, and they are considered to be fundamental and not composite particles. So they really exist in different parts of the landscape of particle physics, because the quarks that compose neutrons are subject to the strong force and quantum electrodynamics, whereas the neutrinos are subject to the weak force and are understood in those terms. They all, of course, have gravity since they have mass.
Excellent. The next question is from Haider Gomez, who asks, do you consider that the future of space exploration will be based on robotics and artificial intelligence, which simulate humanoids, or will it be humans?
I mean, humans are expensive and fragile to maintain in space. So human exploration of space is always going to be expensive, and if you're looking to do it the cheapest way, you'll always use robots. And it is true that robots are getting better and better, and AI is getting better and better. So our ability to have remote observations by essentially sentient robotic entities that we send out into space, they operate almost autonomously and don't really need much from us, but we'll report back the results. I think that is the future of space exploration.
The next question is from Shamsuddin, who asks, according to Stephen Hawking, black holes emit rays, Hawking radiation, but the black holes attract light. So how is it possible that they emit radiation as well?
Well, black holes attract light, they attract matter, they draw in anything in their surroundings. But at the event horizon of a black hole, there's a process called pair creation, which is a product of the vacuum of space. It's present anywhere in space, not just near a black hole, where you have vertical pairs of particles and antiparticles coming in and out of existence all the time. And when that process happens at the event horizon of a black hole or near it, there's a finite chance that one member of the pair will be trapped in the black hole and one member of the pair will be outside the event horizon and therefore able to escape. And so that's Hawking radiation. That's why you have some radiation, very small amount of radiation coming off a black hole. But indeed, most stuff near a black hole is headed in and will never come out.
Elaine and Elizabeth Bojarski, or that account, asks, I recently read that the estimated size of the universe is around 40 billion light years, although the observable size is only 13.8 billion years. So how is this 40 billion light years distance established?
Right, the number is probably closer to 39 billion, but it's about 40 billion. And so the question is, how can you have a universe that is where the distance to the horizon or the edge of our vision is 40 billion light years when the universe has only been around for just under 14 billion years? And the answer is because in the first phase of the expanding universe, especially the first third of the history, the first 4 or 5 billion years, every point in space-time was moving away from every other point in space-time faster than the speed of light. And so that means after the cosmic expansion has slowed down, you have regions that you can see, they're still within your range of vision, whose distance is much larger than you would expect by simple light travel time, because the universe was expanding faster than light. That's really where that extra factor of 3 comes from.
The next question is from an email. What is negative mass?
Negative mass is a theoretical concept, and it's not a simple physical concept because everything in the universe in standard physics just has mass and an equivalent amount of energy, and that's it. Negative mass is a theoretical concept that comes up in some theories, but I think as a general concept it's not particularly useful because it doesn't apply to any astronomical objects that we study in astronomy.
Sorry, the next question is from Bakuja, who asks, how does somebody get permission to view at at a local observatory?
Well, most observatories, small observatories, the big telescopes tend not to be open to the public for any reason. Their time is so valuable and astronomers compete for it that it's really hard to have public viewing. But at local observatories and small observatories, they almost all are interested in outreach. The people who run the telescopes are really keen to show people what they can see through the small telescope. So you basically just have to look at the website of the name of the observatory, and I'm almost sure for almost all of them you'll find public viewing nights. They'll tend to be around when the new moon is, when you can see more stuff, but it's just look on the internet at the websites of these observatories, and I'm going to bet there are public viewing opportunities.
The next question is from Yang, who asks, if pulsars are seen head-on or perpendicular to the telescope, would there be a visual difference?
So pulsars are indeed seen along the beam of the pulses, and the pulse emerges from hotspots on the surface of the neutron star. Those hotspots do not have to be on the spin axis or at the polar regions. They can be offset from the polar regions. So when you're seeing the hotspot and the radio emission from it, synchrotron radiation sweeping through the beam of a radio telescope, that's what you're seeing with the pulsar. So it doesn't tell you directly what the spin axis of the pulsar is, for example. In terms of what you would see visually, the answer is not much or not anything, because neutron stars, they emit this due to imperfections and blemishes in the surface. They emit cyclotron radiation, which is pretty low energy radiation, but they don't have a mechanism to generate optical emission. And so only a handful of pulsars have been seen optically. The Crab pulsar is, of course, a prime example of that handful because it's one of the most famous pulsars. But optical radiation is very rare in a pulsar situation. Just there's not enough energy being generated near the surface to create visible light.
The next question is from a live participant who'd like to know, what do you think about the possibility of considering space-time as a dense fluid?
Well, space-time is, for the most part, it's a vacuum. Space-time is a medium that is very low density because intergalactic space is most of space-time. That's what fills most of space-time. And so space-time has a very low energy plasma in intergalactic space. It has the microwaves from the microwave background, which is a very low energy bath of radiation. And that's really all space-time has. So it doesn't really have the behavior of a dense fluid. It also has dark energy, which is responsible for increasing space-time exponentially, or in a sort of accelerating manner. And dark energy doesn't really have the behavior of a normal fluid either. So there's nothing particular in space-time that would lead you to apply sort of dense fluid physics.
The next question is from one of our live participants. Why is it that most of the stars in the Milky Way galaxy seem to have stabilized, I assume they mean orbitally, and are not constantly colliding with each other?
Because the Milky Way is a pretty old system. So the Milky Way formed 12, perhaps 13 billion years ago. Though there are new stars forming in the disk, the halo and the oldest component of the galaxy, which is spheroidal, formed a long time ago. And those stars have been stabilized in their orbits for a long time. Stars in the disk are in a different situation because new stars are forming out of gas and they're interacting with each other, and there are sometimes collisions. But generally, there are very few star collisions. The space between stars, even in a region like the neighborhood of the Sun, which is in the disk of the Milky Way, and so a fairly dense part of the galaxy, the odds of stellar collisions are extremely low. They happen very, very rarely. So star collisions really don't mean very much in the evolution of a galaxy because they happen so infrequently.
Blue Jersey, who's on with us live, asks, how is it that we are able to take images of galaxies, say the Sombrero Galaxy, from the side view?
We are only able to take images of galaxies in the orientation they have in space. So unfortunately, we don't have the ability to get any other different view of a galaxy. For the Milky Way, we're kind of stuck with our interior view, and we don't get to see it from above and see the beautiful spiral arms laid out. And that's true of all the galaxies in the universe. All we get to do is see them in the orientation they have. Now, those galaxies may be pivoting and rotating and orbiting in space, and so eventually, if you were patient enough, in millions or hundreds of millions of years, you might see them at a different angle. But for the moment, we only ever see them in one orientation.
The next question is from an email. When did the black hole Sagittarius A star form at the center of our galaxy, and has its position shifted over time?
So we don't know the full history of the black hole in the center of our galaxy. We know how old the galaxy is. The earliest stellar populations in the galaxy in the halo are 12 or 13 billion years old, and we don't actually know if the first seed black hole that would eventually lead to a 4 million solar mass black hole now started that early. That's very difficult actually to determine, because we can look at the black hole mass now and infer all manner of evolutionary paths. It is a fair speculation that galaxies, when they form, have the seed black holes in them at the time they form. And then the black holes just grow at different rates in the centers of galaxies. So it's likely in models that the Milky Way, when it formed 12, 13 billion years ago, had a few hundred solar mass black hole, and that black hole grew very steadily, but actually very slowly, because after 12 billion years of evolution, if it's only grown to 4 million solar masses, it's one of the more modest black holes in galaxies in the universe.
Then Venustic, who's on with us live, has kind of a theoretical question about what would actually change if the sun turns into a black hole. What would happen to things like the climate on Earth? Would it actually affect our solar system?
So in this thought experiment of the sun turning into a black hole instantaneously by some means. It's not going to happen. It's not a real outcome for the sun, but let's just imagine it was squashed. You would basically theoretically be squeezing the sun down to the size of about a golf ball, and that would meet the formal definition of black hole. So an incredible amount of compression. Well, at that point, of course, the radiation from the sun would go away completely. But the mass wouldn't have changed. So the things that wouldn't change would have been the orbits of the planets, because the gravity of the sun has not changed. Its mass has just been redistributed to a more compact form. So the Earth would continue in its orbit uninterrupted. Will be devastatingly different, of course, is the loss of radiation. And so that loss of radiation would spell the end of the biosphere and life on Earth, and would send the solar system, the whole solar system, into the deep freeze with the loss of stellar radiation.
The next question is from Anjali, who asks a very general question. I think you can interpret it in a variety of ways. Can you talk about whether the quantum world really exists?
Not quite sure what that phrase even refers to, but the quantum world is a phenomenon where we have to understand the way the world works in terms of quantum physics, because it's a very well verified theory of nature. And so there are manifestations of quantum physics, or the quantum world if you like, in all sorts of situations. We see the quantum world arising in astrophysics, in situations in compact stars, in situations near black holes, high energy astrophysics. So as a general phrase, it just relates to the fact that quantum processes occur throughout astrophysics and throughout the universe. And so we have to understand quantum theory and its application to understand how the universe works.
The next question is from Frederick Sherman. Do you believe that time is infinite?
The future of time is a matter of some debate for physicists. We don't really know the fundamental nature of time necessarily, and especially why it's unidirectional and has an arrow. But in the universe that we think we see around us, which is infinitely expanding, we imagine that time will continue to play out infinitely. So if the universe expands and will never be counteracted by any other force, dark energy will force the accelerating expansion forever, the universe getting thinner and more diffuse, then the time arrow and the time axis will just continue throughout that. So in the modern cosmology, time is indeed infinite in the forward direction, because there's no physical mechanism to understand in terms of why time would suddenly cease to exist.
The next question is from Zodin Puya, who asks, according to the theory, as one approaches the speed of light, time appears to stop. If this is the case, then the distance traveled would be zero. Can you talk a little bit about how these things relate to each other, time traveled and distance and that kind of thing?
So in special relativity, as an object moves towards the speed of light, the time measured by that object, assuming a macroscopic object that can keep time through a clock or an atomic clock, then that time will appear to slow as seen by an external observer. Also, lengths will contract in the direction of motion. That's the Lorentz contraction. And also the mass of that object will increase. So these are three physical effects of special relativity caused by motion close to the speed of light. So two things are happening. Time is slowing down, that's time dilation, and lengths are contracting, that's the Lorentz contraction. And those two things, since speed is distance divided by time, they conspire to leave the speed of light the speed of light the same regardless of the direction of motion.
Excellent. The next question is from one of our live participants. That Human asks, hello, Professor. Is the quantity of dark matter throughout the universe fairly consistent, or does it come in noticeable batches of more and less dark matter? And if so, at what scale is this noticeable?
So the fraction of dark matter on a cosmic scale relative to normal matter does vary. There is a variation. There is a cosmic mean, though, and the cosmic average is essentially a factor of 6. So about 4% of the physical universe is baryonic material, protons, electrons, neutrons, the stuff we're made of, and all stars. 24% is dark matter, and the remainder, almost 2/3, is dark energy. And that those factors, 4% and 24%, or a ratio of 6 to 1, they do show some variation on different scales. The biggest variations are on the scale of individual galaxies, where some galaxies can have 2 or 3 times more dark matter relative to normal matter as others. But as you get up to the larger scales, the cosmic mean seems to be preserved, where most clusters of galaxies, the largest bound objects in the universe, have roughly the same amount of dark matter. And we just assume it's a complex cosmic history involving collisions and interactions and mergers that leads to these variations.
The next question is from Birhane, who asks, is time travel possible?
Not that we know of. Time travel would involve going backwards or forwards in time, and time travel would require us to violate causality, essentially, because as soon as you can go forward and backward in time, you can interfere with the normal physical process whereby every event has a cause, and you can identify the cause. If you are able to go back in time, you can change the causes of something, and especially if you can do that at will. And so the real reason people, or physicists, think that time travel is impossible is because it would violate this foundational rule of causality. Because if you think about the hypothetical, if there were no causality, if events didn't have identifiable causes, then essentially it would be a fully chaotic universe. It would make no sense.
The next question is from Faisal, who asks, is it possible to determine the ages of black holes even approximately?
It's a difficult thing to measure the age of a black hole because the black hole doesn't really have its history written on it in any particular way. A black hole is kind of mute to what caused it to be there. Because again, a black hole is a tomb of matter. All the stuff that went into it is invisible, and so you can't see inside it, you can't see what it was made of, and that also stops you from seeing the history of how it was constructed and what went into it. So for that reason, measuring the ages of black holes is very difficult. And even inferring their age from their rate of growth is difficult because we don't really measure very accurately the rate of growth of any black hole, stellar mass or supermassive in the center of a galaxy. So actually the ages of black holes are very poorly determined in general.
The next question is from a live participant. How is it that we can measure the luminosity of distant stars so accurately to determine their distances? Why don't these measurements get corrupted with the Earth's atmosphere or stardust in between the Earth and the star?
So the measurements of these precise quantities can get corrupted. The Earth's atmosphere impedes a lot of observations and interferes with their interpretation. But basically, it doesn't interfere with the mechanisms by which you calibrate the distance or luminosity of an object. So astronomers have methods for measuring distances and luminosities that are based on foundational physics or astrophysics, and so that those are not corrupted by the fact that you're observing through an atmosphere. The quality of the data and the type of data may be affected, but the physics behind an inference of mass or luminosity or distance or size, the things astronomers want to measure, is not usually affected by the atmosphere.
The next question is from Saruba, who asks, sorry, I'm trying to kind of reinterpret the question here. So the question is about determining the composition of asteroids. Can you discuss how we know what asteroids in various places in the solar system are or might be made of, and whether that changes based on whether they move throughout the solar system or where they were formed and things like that?
So there are different spectral classes of asteroids, and they relate to their composition. Some have written them are highly metallic, some of them are have a lot of carbon-rich material, some of them have more silicon material, and some of them have a lot of soot. They're actually not just because of rocks themselves, but actually because of pure carbon itself in the form of graphite or soot. And all of these measurements are based on reflectance spectroscopy. So basically, we see reflected light, dim reflected light from asteroids. We measure it into a spectrum, and that allows you to do mineralogy. That allows you, with some limitations, to decide what minerals the asteroid is made of. This data is not always of a very high quality because asteroids are very far away and they're very dim. So it is not a precise science, but you can certainly measure the reflectance spectra of dozens or hundreds of asteroids and form population averages, and so see different families of asteroids. And what's interesting is when those families get related to their orbital properties, because then you're starting to talk about how those asteroids were formed, and that's how asteroid science moves forward.
Excellent. It is 11 o'clock. I think we will take one final question before we wrap up for the day. Lukas Fellner asks, hello, Professor. There are some orbits of trans-Neptunian objects suggesting that there must be another planet, Planet X, outside Neptune's orbit. Are there any other explanations for the unusual orbits of these trans-Neptunian objects?
It is true that trans-Neptunian objects, that's objects pretty much in the Kuiper belt. The Kuiper belt extends from 40 to 80 astronomical units, so the trans-Neptunian objects are in this realm. And certainly the orbits of some of them could lead you to infer the presence of a significant mass planet. But actually those measurements are quite uncertain, because any particular trans-Neptunian object's orbit could have been influenced by any number of things, and it's not obviously caused, if it, say, deviates from the ecliptic plane, for example, it's not obviously caused by a single object. So you have to make an assumption before you can go from trans-Neptunian orbits and their particular properties to the presence of dark objects and Planet X, say. And those assumptions, and simplifying assumptions essentially, are what mean there's always some uncertainty. So I would say at the moment there's no evidence for an object certainly of the size of Uranus or Neptune in the trans-Neptunian space. There is evidence, however, for half a dozen, maybe a dozen or more objects that are about Pluto mass, dwarf planet size, in the trans-Neptunian realm, and many have been discovered in the last decade. Thanks for the questions, good as always and varied as always, and I'm not sure on our next live session schedule. We may not have one on the books, but we'll be back with you in a couple of weeks. Thanks to Matthew for facilitating.
Excellent. Thank you very much, Chris. And thank you, everyone, for joining us. Please make sure you, again, like and subscribe, like the video and subscribe to our channel so you can hear about upcoming live sessions. We will let you know as soon as possible when the next one will be. Take care, everyone, and have a great rest of your week.